We're now in section 4.2, and this section is titled Modeling with Quadratic Functions. This phrase we haven't even talked about yet, but we will. What type of functions are quadratic functions? And we're going to start by thinking about that example of tossing up an orange again. So here we have a function that's modeling the height of an orange that was thrown up over time, and again it's seconds. This one's slightly different than the last one we looked at. It was just thrown with a different force and it hits the ground at a different time, but basically this orange was thrown up, and you can see already the highest point, it reached 9.891 feet at 0.656 seconds, and then it hit the ground at about 1.442 seconds. And over here we have a table with a bunch of values for every tenth of a second where the orange was. The first tenth of a second it had gone from 3 feet where it was initially thrown to 4.94 feet. You can see how it grows and grows. You also can see every tenth of a second how the rate of change changes, because here in this tenth of a second here it goes fairly high and then less high the next tenth of a second, and then less high and then less high and then less high. Again, this is because gravity is working on it, so it's not going up quite as fast. Now, the thing I want to look at is this is the function here. So here we're seeing a function that's definitely not linear because it has this x squared term in it. This is different than anything that we've seen before. And what I want to explore for a minute is what happens if I change this last number here. So we're going to change this and call it, instead of 3, we're going to call it A. And Desmos lets you add a slider where you can adjust what that A is. So let's take it back to, okay, so here A does equal 3. So we're back to the original function. This is what it looked like. These purple dots are where the height is every tenth of a second. When this A changes, which I'm about to change it in a minute, I'm going to hit this play button. What does that change about the function, and especially what does that change about the graph? So watch this closely. We'll go a little bit slower here. And if you had to describe as we change this last number in the function, this constant term, what is that doing to the function itself as it changes? So here, right here, A is 2.55. What is that representing, this number? Actually, I'm going to call this C because we are going to call it C in a minute. And we'll go slow again. Okay, so you're probably seeing what this constant term is doing to the whole graph, how it would change it, how it would affect it. When C equals 2, where is the y-intercept of this graph? Oh, it's right at 2. When C equals 5.5, we see that the y-intercept is at 5.5. When C equals, negative 3, we see that this graph, this parabola-shaped thing, has a y-intercept of negative 3. In this function here, the C represents the y-intercept of the function. Okay, we're back to our old standard function, negative 16x squared plus 21x plus 3. And this was what it looked like. And we're remembering that this is the height of the orange over this many seconds. I want to explore now this number here, this 21. It represents something also. And we're going to look at what happens if this number changes. Okay, so I've added a parameter b, and we're going to let this b change between negative 25 and 25 and see how that affects the look of the graph. Remember when we changed the 3, what it did was it was shifting the graph just straight up and down, and it was affecting this y-intercept. This number we know on the end is the y-intercept of this function. When we change b, it's 21 right now, and that's what it is in the original function. Let's see how that affects the graph. So I'm going to play this. So what is it that's changing as b changes? Interestingly, our y-intercept stays fixed at 3 because this 3 isn't changing. But this middle number is changing b. Right now it's a negative number, and all of a sudden in a minute it's going to change positive. So what is it that's changing from negative to positive? So now it's 6, 7, 8, 9, 10. You know, in the original function, that b was 21. Oops. So let's take it back to 21. About right there. What I want you to pay attention to is how is the rate of change of the graph at this this initial point, which is when time equals 0. Think of the rate of change as almost like the slope of this graph. It's getting steeper, steeper. Okay, now it's getting less steep, definitely less steep, and all of a sudden that slope, that rate of change right about now is going to become negative, right at that initial value. And it's going to become even more steeply negative. So as it's negative 25, and now less steeply negative. Let's see what happens when b equals 0. Let's take it to 0. Okay, when b equals 0, you can see that the if we were going to take a rate of change, like an instantaneous rate of change right here, that it would be probably a horizontal, you know, it would be, the slope would be 0. If we move it up just a little bit positive, maybe to 2, that slope, that instantaneous rate of change is growing slowly. And when we take it up more dramatically, that instantaneous rate of change right at the initial value of t equals 0 is growing, and right here is when the instantaneous rate of change is about 25. So what we just saw was this number right here, which is 21 in our original problem. This is representing the initial rate of change when x is at 0. So whereas this guy here, this number represents the actual y-intercept, this guy represents how the function is changing at that y-intercept. You know, the instantaneous rate of change, or you can think of kind of the slope of the function at that initial value of x equals 0. So this 21 was representing the instantaneous rate of change at x equals 0. And this negative 16 has a significance too. We'll talk about that in a minute. But let's generalize what we've found so far. Do you remember a long time ago we talked about this library of functions that we were going to be looking at this semester? And we've spent a lot of time in Chapter 2 talking about linear functions. We're now here in Chapter 4 dealing with what are called quadratic functions. So we're already on this second book in our library of functions. So we've seen this one example of a quadratic function here, and let's generalize this and talk about what the form of a quadratic function would look like. So a quadratic function in standard form looks like this. You have f of x equals ax squared plus bx plus c, and the important thing is you have this x squared term. So a, b, and c are just going to be some real numbers. But a quadratic function, you have an x squared term. And remember, linear functions, really all we had was this part of this function. But now we're introducing a new term, and that's going to really change things. It's going to create these parabolas instead of straight lines. And we might have a parabola down or a parabola up, but quadratic functions always look like parabolas. So just taking a minute to look back on linear functions, remember that this number here, whatever it was, it represented the slope, and this number here, whatever it was, it represented our y-intercept. So what we saw in the orange example is that for this general quadratic function, this constant term, this c on the end, is going to represent your y-intercept. This b right here, whatever this number is that's tagging along with the x, this number is going to represent your instantaneous rate of change at the initial value when x equals 0, or maybe t is that independent or input variable, whatever the initial value. Initial value just means when x equals 0. And then this a, which we haven't really talked about yet, let's look and see what happens if this number changes. Okay, so I've substituted that negative 16. I'm calling it a now, and down here I'm telling Desmos, hey, let a equal negative 16, but also we're going to change it up a little bit, and it's going to equal other numbers too. So as I push play, see what happens to the graph, and what I really want you to focus on is what happens when a is positive and what happens when a is negative. So still negative, still negative. We're pretty close to, okay, it's positive now, and it's a totally different number. I mean, it's a totally different graph. So let's zoom out for a minute and see what's happening. Here, a is positive. Let's see what happens when it flips to being a negative number. As soon as it flips to a negative number, it became a graph that was really concave down. Whenever this number was negative, it was concave down. Okay, we're zooming out a little bit more just so we can see even more what's happening. And now it's about to turn positive. And as soon as it turns positive, it flips into concave up. So for now, what we'll remember is that when this number is negative, it's a concave down graph. And when this number is positive, it's a parabola that is concave up. So when a is positive, we get a parabola that looks like this, and when a is negative, we get a parabola that is concave down. So each of these numbers here gives us a clue as to what the parabola should look like. Let's look at a couple more examples. If this is our quadratic function here, we can kind of sketch it before we even know too much more about it, just based on these numbers. And this number right here is an implied 1. It's not written, but whenever you have a term that doesn't have a coefficient, it's implied that it's 1. Okay, let's start with the negative 5. So the negative 5 tells us that whatever this parabola is doing, it's going to hit the y-axis, 2, 3, 4, 5, right here at negative 5. Now this 7 right here tells us what the instantaneous rate of change at that point is. This is sort of like the slope of the function at x equals 0. So right here as the function, this parabola, and maybe we should talk about this one first. This is a positive 1, so that tells us that the parabola is going to be shaped like this. So we know the parabola is shaped like this. We know that it hits right here at negative 5, and we know that as it hits at negative 5, it has an instantaneous rate of change of about 7. So that's like the slope of the graph at 7. So think about how this could be going down. I mean, this parabola, we know it has to be going concave up. So it's got to look something, we don't know exactly where it bottoms out, but it has to look something like this. So just based on those three numbers, we know that the parabola should look something generally like this. And let's go ahead and graph it on Desmos and just see how close we were. Here's the function. When I graph it on Desmos, this is what it looks like. And we were fairly close. We knew that it hit at the y-axis at negative 5, and we knew that it should be have this kind of rate of change at negative 5. Like I said, we didn't know exactly where it was going to bottom out, but we knew that it was concave up. So each of these numbers, the implied 1 here, the 7, and the negative 5, gave us really good clues as to what the shape of this parabola would be, this quadratic function. Okay, so I just moved this guy over here. Let's do one more quick example like that. And this time our quadratic function is negative 2x squared minus 5x plus 1. Each of these numbers will give us some clues. So the negative 2 tells us, is it opening up or down? Is it going to be concave up or down? And this negative definitely tells us that this parabola, whatever else it's doing, it's shaped like this. It's going down. It's concave down. That's the big clue from this first parameter. Then this guy right here is telling us when it hits the x-axis, wherever it hits, it's going to be traveling at an instantaneous rate of change of -5. It's like a -5 slope as it hits that y-axis. And this last number tells us exactly where it does hit the y-axis, which is at 1. So let's see, let's put all that together. We know, first of all, that it hits the y-axis at y = 1. That's the y-intercept. And that's just from this number here. We know that as it hits the y-axis, that its instantaneous rate of change is this number here, -5. So as it hits, it has this sort of negative slope, this negative instantaneous rate of change. And it's fairly steep, it's -5. Remember that, you know, this would be more like -1/2, 1, 2, -3, -4, -5. So it's fairly steep, this instantaneous rate of change. So we know the graph is going through, as it goes through that y-intercept, it's traveling something like this. And the last guy is telling us that this parabola is definitely going to be upside down. It's going to be concave down. So this parabola, there's only so many options. It's traveling something like this. We don't know how high it gets, but we know that it's concave down, and we know where it hits the y-axis, and we know fairly certain what it looks like as it hits the y-axis. So let's go ahead and graph this on Desmos and see how close we were to this one. Okay, I've input the function, our quadratic function, into Desmos, and I'm going to hit this little circle to graph it. And that looks pretty much like what we thought it should look like based on all those numbers that we know what they represent. So at this point, we definitely want to remember that this is the standard form of a quadratic function. And all of these numbers represent different pieces to, when you graph it, what it should look like. At this point, we need to pause for a minute and think, why are these even called quadratic functions? The distinguishing feature of them is that they have this squared term. So why aren't they called squared functions? Where did the word quadratic, how did that become associated with this form of a function? And the answer is that quadratus, is Latin for square. And one of the reasons this second power is even called squared in mathematics is because when you're dealing with the area of a square, you square the sides, right? I mean, you take the second power of the sides, of the length of the sides, and that has become known as squaring a number. It's all related to the area of a square. So these functions are tightly connected to problems with squares, like finding the area of a square, etc. So when you see the word quadratic, sometimes you think of the number 4, because quad, you think of 4, but and a square does have 4 sides, but this quadratic functions are always have this, the input variable is squared. That's the distinguishing feature of a quadratic function, and it really comes from in olden times when they were finding the areas of squares, which was taking the side of a square and multiplying it by itself. We're now going to pivot and talk about a new topic, first and second differences. It's still related to quadratic functions, but a topic that we need to discuss. So let's think about this function here. F of x equals 3x squared plus 8.6x minus 7. This is definitely a quadratic function. We have this x squared term here that tips us off that we're talking about a quadratic function. And we can think about what we would expect this function to look like. This -7 right here tells us that that's the y-intercept. So let's see, -7. The graph is going to hit right here. And then this 8.6, this is the rate of change, the instantaneous rate of change at the y-intercept. So it's kind of like the slope of this function, how it's behaving right there. And so 8.6, that's a pretty steep slope, and it's a positive slope, so we would expect this function to be going kind of like this at this point. And then this 3, the a term, tells us that we can expect that this parabola is going to be opening up because it's a positive 3. And so this parabola, this quadratic function, we kind of expect it to look something like this. Again, we don't know exactly where it bottoms out, but we know its behavior right here at the y-intercept, and we know that it opens up. So now I'm going to have Desmos graph this, and we'll see how close we were. Here's the function, and we were pretty close. It opens up, it hits right at x equals -7, and it's got this instantaneous rate of change at that point that's pretty steep, this 8.6. Now for a minute I want to look at a table of values for this function. So this table here is a table of values for our function, and we can see that when we have -5 as an input, 25 is going to be an output. I guess we can't see it on the graph right here, but we can see this one. When -4 is an input, 6.6 is an output. So when -4 is an input, 6.6, which is right there, is an output. Yeah, that's a point on the graph. And -3, -5.8, 1, 2, 3, -5.8, that's a point on the graph. -2, -12.2, 1, 2, -12.2, and -1, -12.6, and 0, -7, we already knew that guy. Okay, so essentially this is a table of values of this function. So now here's what I want to think about. I want to think about these outputs, and what if I took each output and subtracted from it the one that came right before? So this output minus this one, and then I would do this one minus this one. These are all evenly spaced inputs. If we took the difference of the outputs, you know, each successive pair, if it was a linear function, they would be the same number actually, but it's definitely not a linear function. We've got this parabola. But let's take a look at, these are called first differences. When you're taking just the difference of the output, you have an evenly spaced set of inputs, and you're looking at just those differences of the outputs. They're called first differences. It's not an average rate of change because we're not dividing by anything. We're just looking at the difference. So we've done what we said we were going to do. I took 6.6 and subtracted 25, and I get this guy. I took -5.8 and subtracted 6.6, and I get this number. I took -12.2 and subtracted -5.8 and got this number. And this one's easy to see, -12.6 minus a -12.2, and I got -0.4. Okay, importantly, these numbers are all different. So this function is not a linear function. They're all different, but you can probably already see something that's happening. If you look at the differences of the first differences, like if you were going to take differences here, do you start to see what's happening as I jump from one to the other? There's a constant number that's being added each time. So now I want to go slowly through this, but this new column here is what are called second differences. And essentially what I did to find them is I took the first differences subtracted from the first difference of the term before. So 41.6 minus 35.6 is equal to 6. 35.6 minus 29.6 is equal to 6. Each of these differences is 6. And of course you're seeing that we're getting a constant second difference. Where a constant first difference tells us it's a linear function, a constant second difference like this tells us this is a quadratic function. So let's take a look at this whole big rigmarole table thing one more time and make sure we understand where each piece is coming from. We had this original input-output table, and it just followed the function. That's where all of these numbers came from. And they were points on the graph. So these are just our input-output table of values for the function. Then we decided, hey, let's take differences. So we did this output minus this output minus this output, this output minus this output, and that's where these numbers were coming from. They weren't constant, and so that told us immediately that this cannot be a linear function, because a linear function would have constant first differences. But then we decided to keep going one more step, and we said, okay, well, let's take this guy minus this guy. And these are called second differences. They're the differences of your differences. And as we took those, and it's hard to see with negative numbers just because you gotta really think through the negatives, but you can see more obviously in your head, 11.6 minus 5.6, oh, that's 6. 17.6 minus 11.6, oh, that's 6. 23.6 minus 17.6, that's also 6. And every time we were taking these second differences, so the differences of the differences, we were getting a constant number. And constant second differences will indicate that you have a quadratic function. We definitely did. We knew that from the beginning. But this example, I just wanted to illustrate that, first of all, what these things are when you see them, these terms first and second differences, and that a constant second difference will always indicate a quadratic function. So if all you have is a table of values, you can still determine if this is a quadratic function by taking first and second differences. And that's what we have here. When I say constant second differences, it means that the second differences are always the same number as they are here. It's always 6. In another problem, it might be like 8 or 7. But these constant second differences tell us we have a quadratic function. Okay, now an awesome topic, quadratic regression. Do you guys remember when we did linear regression, you would have some data points and you thought maybe these, kind of were close to a line, and what would that line be? And that would help us predict things in the future. Well, quadratic regression is the same idea, but instead of data that looks like a straight line, you might have data that looks sort of like a parabola. And maybe it doesn't fit exactly a parabola, but maybe it comes pretty close. And you could find the parabola that is closest to all those points. And then you would, again, be able to predict data that you don't already know, whether it's from a table or whatever. And so this is the idea of quadratic regression. Okay, we're going to use this example. Use quadratic regression to answer the question. And we have a table, this is out of your textbook. We have a table of NFL players' salaries, and the input is years since 2000. So this is indicating 2000, 2001, 2002, etc. And these are NFL player average salary in thousands of dollars. So in the year 2000, the average salary for an NFL player was $787,000. And then the question they want us to ask is, what was the NFL player average salary in 2008? And that would correlate to x equal 8. We don't have that in the data table, so we're going to use quadratic regression to discover what the output value would be if the input value is 8. And someone could ask, why use quadratic regression? Why don't we just use linear regression on this? Well, when I look at the rates of change between these output values, I'm seeing, this is almost 200 here. But by the time we get down here, it's only about 70 is the difference. And so it looks like we have a table with variable rates of change. We're going to go ahead and plot this data and take a look at it. Usually you plot the data and you can kind of see what the general shape of the graph is and then decide what type of regression you want to use. Okay, we're going to do our quadratic regression and we'll enter the data into Desmos. So we'll look for a table and we'll go 0, 787, 1, 986, 2, 1180. Okay, the data is all here, and now we're going to tell Desmos to do a quadratic regression. And so we start Y1, and then we look down for the little tilde. Here it is. And then we have to not tell it to do a linear regression, so we need to give it the standard form of a quadratic regression. And we'll say A x1 squared plus bx 1, we're always using x1s, plus c. And it is giving us a quadratic function. This totally does not look like a quadratic function, but we just need to zoom out and we'll see that it actually is. And what we're going to do is we're going to change over here the x-axis. I don't really need it that wide. It looks like we're going from, let's go -10 to maybe 20. But the y-axis, we definitely need to get it a lot higher. So let's go up to 800 on this. Okay, looks like we need to go a little bit higher. We'll go up to 1200, even higher. How about 2000? Okay, that looks good. Okay, so it took me a little while. I guess, why did I even go through that? I could have just done zoom fit. That's all I needed to do right there. Either way, you can do it manually or you can hit that zoom fit. So they have found us a quadratic function. The green dots are the actual points in the data table, and we had a hint that it wasn't going to be a linear function because the rates of change were so variable. And so it looks like a quadratic function does fit this data pretty well. Now the question they ask is, what's the average NFL salary in 2008? So we really want to know, what's happening when our input value is 8 right here. What is the value up here? And there's different ways you can do this. You can kind of click on it and get a number. There it is, 1258.414. Or a foolproof way is saying, okay, let's draw the line x equals 8. And that's this black line, and let's see where those intersect. And so it looks like this is the answer to our question here. So let's take a minute and look at everything that's going on with this graph and this data. Along our horizontal axis is years since 2000. That was the input for the function. And then along the vertical axis, we have average NFL salary. And that was this data here. It all came from this table here. We decided to try a quadratic regression, and this is the form that you need to put in when you want to use a quadratic regression. The reason we decided that was because these differences, they were really variable. And we've got this fantastic R-squared that tells us that the data is actually pretty close to that curve. So that checked out that this would probably be a good model for things. And then we were asked what was the NFL player average salary in 2008. And so we looked at when x equals 8, and we found this solution here. Now, there is a small problem with this model because realistically, salaries are probably not going to go down. So we'll see other models in the future, but this maybe is better as a logarithmic model that keeps growing. But it's definitely, it's definitely fitting this data for now, and we just have to kind of take it with a grain of salt, knowing that salaries aren't going to go down. But that's part of, the whole modeling process is deciding if your model is a realistic model. It definitely fit the data in this case, but as far as does it really predict the future, that's something that in this case, it probably is lacking in that area. So for now, we'll simply answer the question they asked. They asked us to use quadratic regression to answer this question. What was the NFL player average salary in 2008? And we'll answer, it was 1258, and this is in thousands. So 1258, 414. So 1.2, about 1.2 million is the answer to their question. One last thing is we should actually write out what the model is. The Desmos found the parameters for us, and we need to write out the function.